All right, so you can all hear me pretty good, right? All right, so let's get things started. So you guys all got my announcement yesterday regarding the assignment 4 submission. So the new date will be next Tuesday. Of course, you're still at the beginning of the class. Actually, today I actually just talked to Dr. Roche, and um, we we will actually give all the students who have submitted the assignment 4 with a little extra credit. So we haven't decided on how much, how many points we're going to give to the students that submitted their assignment last Thursday. Of course, like all of you that haven't submitted, you will get the full mark. Um, you will not get anything deducted, right, as a penalty, right? So, but the new due date will be next Tuesday um, before the class. So, and we're still trying to decide what's going to happen with the midterm exam. Most likely, it will be around next Thursday. But we will see in what kind of format uh, that we're going to do the midterm, uh, or we may not necessarily do a midterm. We could, for the rest of the semester, we could just give you guys a series of quizzes to do, and as replacement for exams. And those quizzes will be, of course, with the online format. Um, so hopefully, we can have a decision on the times for the exams and the format for the exams pretty soon, so we can send out the announcement. All right. So let's start the class today. So today we're trying to finish the memory management unit, memory management topic. Uh, so essentially, we want to finish the topic of paging for virtual memory. So let me see how many students are here already. So I got 20. Okay. All right, so last time we talked about the page replacement algorithms, right? So we talk about there are essentially 3 types of page replacement algorithms. The ideal one would be the optimal. Optimal means that you kind of know the future, right? You kind of know over the next little while what kind of memory access you're going to do, so that you can, based on that, you can determine which page you're going to throw out in the page replacement. Of course, you're going to throw out the page that you won't be accessing for the longest time, right? So of course, you don't have that knowledge, right? So the optimal algorithm is more or less sort of being used as a benchmark, right, for you to compare with other page replacement algorithms. And of course, the simplest algorithm would be FIFO, right? First in, first out. And it's pretty straightforward. And the third type would be LRU, the least recently used algorithm. And essentially, that's the one we need to be focusing on. So we talk about a lot of LRU implementations. There are sort of approximations of the perfect LRU, right? Because you can't, if you try to track the least recently used pages, like in a perfect way, you have to remember, the timestamps of the timestamp for each page, for each memory access, right? That just adds a lot of overhead to to the system, and that's not practical. And also, you think about with perfect LRU, for every memory access, right, you have to remember which page you access, and you associate a timestamp with that page for every memory access. Also, you need to keep a sort of a ordered list, right, to remember uh, those recently accessed pages. So perfect LRU is not practical, so people came up with all these approximations of list of LRU. Of those, we specifically stressed on two of them. One of them is not frequently used with aging, and also the other one is the work set clock algorithm that we talked towards the end of the last class. So those are the two mostly used in the real world systems. The NFU with aging and the work set clock. All right, so yeah, so we already talked about the simulating LRU is essentially not frequently used with aging. So all right, so as we finish talking about all these algorithms, we need to have a quick summary of all these algorithms. As I essentially just did that. So what we need to focus on is the ones that are approximations of LRU. And especially, I would encourage you guys to do some exercises with the NFU with aging and the working set clock algorithms. You guys can review the book, and I think those are very good test materials. All right, before I move on, I don't want, I don't want to spend too much time on what we already talked about. Before I move on, anybody having any questions about the page replacement algorithms? If you have, raise your hand. All right, so, okay. All right, so let's look at, we're gonna, so this is a new for today. So, so as we talk about, with page replacement algorithms, naturally people would think, because why do you need page replacement, right? So, well, as programs get loaded into memory for execution concurrently, it would use it could use up all the available physical memory space, right? Sooner or later, right? Your physical space could be filled up, or even a single program, right? As we talk about, it could use all the physical memory. Even a single program could use all your physical memory, right? Because as the virtual memory space can address like a much bigger space than what your physical space, physical memory space can provide, right? So even a single program can use more memory than your physical memory provides. So after your physical pages are filled up, after that, if a process refers to a virtual address in a virtual memory page that is not mapped to any physical frame in the main memory, right? What are you gonna do? So you're gonna incur, that will incur a page fault, right? So we talk about the page fault is, we're gonna go through the details about how a page fault gonna be, is handled later on today in this class. But first, let's think about what a page fault, when you have a page fault, what you're gonna do. in the case I just talked about, if your program is trying to access a page, a virtual address that is not loaded into the physical memory yet, that means that page is sitting on a disk. So you need to bring that page in, right? And meanwhile, you have your physical space already filled up. So you're gonna have to kick out a page, right? So that's a kick out existing page residing in the physical memory. So that's what we call page replacement. So why do we need page replacement? Because we don't have enough physical memory, right? To take more virtual memory, right? So normally people would think, okay, in that case, if I add more physical memory to the system, right? So if I add more physical memory to the system, then I would have less page faults, right? Right? You have more physical memory to work with. So naturally, you would have less page faults, right? Well, I mean, is that true? That will be definitely the case for all the page replacement algorithms. It turns out it is not necessarily true. So let's walk through this example here. So, so with this, so you guys all see this, this table here. So let's walk through a FIFO algorithm that we apply here for a series of memory access for this example. So the first row, again, we did this exercise last time, right? The first row is the next series of virtual memory page access. Your process is gonna access. So you have virtual pages on the first row here: A B C D, A B E, A B C D E. That's your virtual page access for this sequence. Now you only have 3 physical frames in your system, right? So let's look at the upper portion for this table, okay? So let's assume you only have 3 physical frames to work with first. So starting from the beginning, of course, you don't. This is demand paging. So first, you don't have anything loaded into the physical memory. So you access A, and A is not in memory. So you're gonna bring page A, right, into the physical memory, and then the same for B and same for C, and on the 4th column. And when you trying to access D, page D is not in the memory. But meanwhile, you have your physical memory all filled up, right, with ABC, right? So starting from the 4th access here, you need to use page replacement, right? So with FIFO, let's say this is you're using the FIFO, right? With FIFO, what are you gonna do? You're gonna have to kick out a page. You're gonna have to pick the oldest page, right, that you have fetched into the system, and you replace that page with D, right? What was the page, at this point that you need to kick out? That would be A, right? So you're here, right? So with the FIFO, you need to kick out A and replace with D. Right? So you have, and then the next access is A again. So you just kick out the A, right? So you would have to bring A back in. And meanwhile, you have to kick out the oldest page at that point. Which page was the oldest page at that point? It was B, right? So here you kick out B and bring A back in. And so I won't go through the whole sequence here. So on and so forth. And after this whole sequence access, how many page faults you have? you have 9, right? So you have 9 here. So you have 9 for the upper portion, right? For this case, right? So for this, you have 9 page faults, right? And then we do the same exercise. So we add one more physical frame to the system, okay? That would be frame 4, right? And if you do the same exercise, right? If you do the same exercise, sorry, I need to remove this participant screen here. Sorry. All right, so if you do the same exercise with one more physical frame to work with, right? You actually end up with more page faults with this sequence of memory access. If you count all the page faults here, right? So, and so here, like these are all page faults, right? Oops. Trying to get my pen working. So these are all page faults, right? So how many of them down here? You have 10, right? So does that make sense, right? It's sort of, you have more physical memory to work with, but you end up with more page faults, right? So this goes back to what I just mentioned, that not necessarily you have more physical memory to work with, you would have less page faults. We talk about minimizing the page faults would be the major goal of your page replacement algorithm. So with FIFO here, you end up with more page faults. You could end up with more page faults with more memory to physical memory. That's what we call Belladie's anomaly. Okay, that's so Belladie. He was the guy that first came up with the idea that certain page replacement algorithms not necessarily would incur less page faults with more physical memory. All right, so with that, let's look at another example here. So let's do LRU, all right, or the mean policy. The mean algorithm is optimal. Let's use LRU, and we apply that algorithm on the same sequence of memory access. Okay, so the same thing with let's start with the upper portion here, right? The same thing. You first bringing the 3 pages in, right? ABC, and that will fill up all your physical memory. And starting from the 4th access, you have to use your page replacement, right? And what you're gonna replace here for the 4th access here, you're gonna replace A because A at that moment was the least recently used page, right? And again, we went through the exercise last time for the LRU algorithm. I won't go through the details there. So basically, after this whole sequence with LRU, you have how many page faults? From the upper portion, you have 9 again, okay? So you have these, right? So I have 9, right? So then with more memory to work with, in the lower portion here, you have one more physical frame to work with. You go through the same memory access exercise, you would end up with 8, okay, page faults. So with LRU, you do have less page faults, right? After you have more physical memory to work with. So why is that? Why is that? So there is a certain class of algorithms. It's called stack algorithms. LRU is one of that. So these algorithms, they guarantee with more physical memory to work with, you would end up with less page fault. So here with LRU algorithm, I need to ask why that's the case. What kind of property with LRU algorithm that when you have more physical memory, you would definitely end up with either equal number of page faults or less page faults. Why is that? Anybody can? Yeah. Who wants to provide your input on this? Right. So why having more frames with LRU? Why having more physical memory to work with? That you definitely will end up not more, no more page faults. Anybody? Oh. Nobody? All right. So, well, let's look at this. So, what do you see here from the uh, from these two tables, right? When you only have 3 frames to work with and you have 4 frames to work with, what do you see? What do you see for each at any time? Any at any time for each memory access, what do you see? Uh, you know, the between the upper portion and the lower portion. What do you see? So with more memory to work with, this is LRU, right? So you would, with 4 frames, right? You you would remember at every time you have a memory access, what what do you have in the memory that you've already loaded? Right. So let's start from this the 4th memory access. So at this point you have what, DBC, right? Right. With only 3 frames to work with, you have DBC loaded, right? In the physical memory. What do you have down here? You have ABCD. So DBC is what? Is a subset of ABCD, right? If you look through at every time point along this sequence, you would see all the frames residing in the upper portion is always a subset, of the frame that you of the frames you loaded down in the lower portion, right? So what does that mean? Because with LRU, you always remember the last few recently used pages, right? You always load the last few loaded pages, right? So with more physical frames to work with, you would at least remember the physical frames that you loaded with less physical memory, plus you have more physical frame to work with. You will load the least recently used frame, one more least recently used frame, right? People getting the idea, right? So anyway, so what you have, the upper portion, what you have in the physical memory is always a subset of what you load in the memory of the lower portion. That's why with more physical memory, you can work with LRU or any similar algorithm as LRU. You always end up, you always remember more least recently used pages, right? With more memory. So that's why with more physical memory, the LRU algorithm will always work better or equally with less physical frames to work with. Any question? Any question about this? No? Okay. If you guys want to ask questions, you can just unmute yourself and just talk. All right. Let me just ask. Because I see people are. Anybody talking? And maybe I just muted all of you that you can't unmute yourself. Give me some feedback. Hello?
Myself.
So, okay, you can unmute. This is Kim?
Amy?
Hello? So sorry,
Amy.
who's talking?
I'm talking right now. Amy Petrus.
Oh, Amy, yes. Okay, all right. Yeah, you can unmute. Okay. You guys have any question? No, about this?
I have just one simple question. Is there supposed to be a page fault on E for the last E column for the 3 frame?
Why is that? Well, here, right? Oh, you mean here?
Yeah, for the last one, is there supposed to be a page fault in that column too?
Oops. Let me stay here. So, why do you think here should be a page fault? Why?
Because E is not in any of the frames and it needs to be loaded.
Oh, let me see here. CDB. Right. You're right, I think. So I have D. D is not there. E. Yeah, you would indeed. You have, yes, yeah, you're right.
Okay.
So I think, yes, you're right. So this one actually will, you're absolutely right. So here we should throw out which page, right? Use LRU.
B.
Right? So which one was the least used here? So it's B, right? So yes. So you should, yeah, you're right. Thank you for that. So you should have E here, right? So there should be a page fault here, and the same thing here, right? You should throw out. So for this access here, oh, well, this one is already
Yeah, it looks like that one was there already.
okay. So this one actually you would have, yeah, this one you would have 10 actually. Sorry. Yeah, thank you, Amy. So for the LRU here, you should have 10 page faults with the upper portion with only 3 frames to work with, and with 4 you only have 8, right? So, all right, thank you. All right. Any question about the difference between the the LRU and FIFO working on the why LRU with more physical frames to work with? It always will have equal or less page faults. You guys all understand that? All right. Okay. So let's move on to the next topic here. All right. So, so that was Belladie's anomaly. Let's move on to the design issues for paging systems. So, as you guys know that we have, we always only have a finite amount of physical memory, as I just talked about in your system. So how do you divide and distribute all the physical memory among all the competing processes is an important problem we need to solve, right, in the paging system design. So, well, you could have like 2 kinds of memory allocation policies for dividing the physical memory among the processes. One is called local. Local means like you could only select a page to throw out from the frames assigned to that particular process, which has which has a page fault. All right. So, when we talk about page replacement, right, you have to pick a frame to throw out, or we can call that frame as a victim frame, right? You can pick that victim frame from the frames that get assigned to that process, right? You can pick, like, that's what we call local. But you can also have a global kind of level policy. You can pick a victim frame from any other process in the system to throw it out, right, when it's necessary. So that's what we call global level allocation policy. So let's look at this simple example here. So here, let's say, so let's look at the leftmost column here. So you have all these, you have three processes there, A, B, C, right? So now you have all your physical memory filled up. And then the process A has access to a page that is not loaded into the physical memory yet. So process A tries to access A6, page A6. And A6 is not there, right? So with the local policy, you would have to pick a frame in in process A to throw it out, right? So here, this example, it picks A5, right? So it kicks out A5 and replace A5 with A6. Okay, so so B here is using a local kind of page replacement policy. So that means you can only pick a frame to throw out for the page replacement within the frames for this process, right? But with C here, if we look at the C column here, with a global level kind of allocation policy, you can pick a frame to throw out from another process. So here what it does, it actually picked the B3, right, to throw out and replaced B3 with A6, right? So that's just a simple illustration of what's the difference between local and global, right? So so then we'll look at, which kind of allocation policy would work better, right? So is it the global level or the local level? So usually global level would usually works better. It could work well with your working set size changing a lot over the time, right? As a lot of times with a local allocation policy, it is just not easy to find a good size of physical memory to be assigned to a process. We talk about, what does your process need to work with at a particular time? It needs to have the working set, right, loaded for that process. But the working set is hard to track, right? Normally a lot of times you either, sometimes you could end up with assigning a lot more frames than your working set. Then you're wasting some frames there. Or you could end up with assigning very few frames for your process. Then you're going to have a lot of page faults with that. So with a global allocation policy, you essentially has a pool of memory globally, right? All your physical memory can be used for your process if necessary, right? So global allocation policy works better, like it provides flexibility. It works well with changing work set over the time. But there are also similar kind of problems with global allocation policy, because you could also end up with too many frames allocated for some processes. If a process just at a particular time, it needs a lot of memory, right? So then your system will allocate a lot of frames to that process, but that may end up with interfering with other processes that concurrently are running in the system. So other processes could have very few frames to work with, and that also could end up with a lot of page faults for other processes. Because on a global level, you have this large, you have the memory pool shared by all the processes. You have one process using too much, other processes would have to give. Um, so, so either global or local, they could end up with too many frames assigned to a particular process or too few frames. So, what would be a good way, to divide the memory among running processes? So you could start with some simple approaches, right? You could assign equal share of frames to all these processes. And again, that wouldn't work well, all right? And because you could, some processes, they just need more frames to work with. Or you could assign a number of frames proportional to the process size. If one process allocates a gig of memory, right? Another process allocates 100 meg. So you would assign like 10 times of number of frames to the one with 1 gig of memory. And then the one that was only 100 meg. But proportional allocation also could have problem. Like the key thing is that not necessarily if you have a large process size that you would have a large working set, right? You think about you could allocate, your process could allocate 1 gig of memory for a huge array, but you only work with like a few elements in that array repeatedly, right? As we talk about, the working set is at that particular time, the repeatedly accessed data would be your working set. So the working set for a large process could be small, right? Could still be small. So that wouldn't be, so if that's the case, even you have a big process size, not necessarily your working set is large. So proportional kind of allocation wouldn't go well either for that case. So what would be the best way? It would be, you try to adjust the allocation for all these running processes based on what? Based on the working set size over the time, right, for that process, right? So if you could kind of track the working set for a process over the time, then you use that to try to allocate the physical frames according to the working set over the time, right, for a process. So that's how people came up with this idea. It's called page fault frequency model. So the idea is that, of course, with very few frames allocated for a process, you would have a lot of page fault, right? Your page fault rate would be very high if you only have very few, frames, physical frames to work with. So this diagram just shows you, for this range, sorry, my pen is always not working very well. Okay, so if you only assign x-axis is the allocated frames for a process. If you only assign this many frames to your process, you could end up with very high page fault rate, right? Then you try to add more frames for that process, right? To allocate more frames for that process. Then the page fault will go down, right? And but if you add more frames from this point on, the effect of having more frames that that to reduce your page faults would be diminishing, right? Right. So what's the best? Um, what is a good range of frames to assign to your process? It would be within this range, right? So so this sort of so people came up with this page fault frequency model. Is a essentially this model tracks the page faults for each process over a period of time. Now you can define your page fault rate is how many page faults within the last second, right? You can use that as a metric. You know, over the last second, how many page faults you have for a particular process. If it has a very high page fault rate, you know, with that period of time, you need to add more frames to that process, right? So the page faults would go down. And so people use this model. They try to make sure that you with the allocated frames, your page fault rate will be within this range, right? Right? People get the idea? So there they can sort of use this model to estimate how many frames your process needs for that particular time to work with, right? So this range here would be acceptable page fault rate for that process. So so that was the page fault frequency model that people use to track sort of your working set size over the time for each process, right? Then use that range of you know, acceptable page fault rate and use the corresponding numbers of page frames there to for allocation, for allocating the physical frames to your process to work with. All right, so let's look at some more design issues for the paging systems. So with the global or local allocation policies we just talked about, so can people think like for all the page replacement algorithms we have talked about, which ones they can work with sort of global level policy and the local policies, or which ones can only work with a certain level of policy. So for FIFO and LRU, can they work with both global and local policies? Oh, people are saying yes, yes. Okay. So thank you. Okay, for your input. So FIFO, why FIFO can work with global, right? Local. Or, you know, for FIFO, you could what is FIFO? FIFO is the algorithm is picking the oldest frame, right, to throw out, right? You could pick the oldest frame from the frames within that process to throw out, right? Or you could pick the oldest frame that is in the system from all processes, right? So FIFO can work with global and local allocation policies. What about LRU? LRU is the same, right? LRU, you can throw out the least recently used page within the frames that are allocated for that particular process, or you can throw out the least recently used page among all processes, right? So FIFO, LRU, those are the algorithms that they can work with either local or global level allocation policies. Right, this is what I just talked about, and LRU is the same. And what about other algorithms, right? What about working set clock? Can someone tell me, would that work? Can the working set clock algorithm work with the global level allocation policy? Give me some of your inputs. No. Oh, more people are saying no. Okay. Right. So that's correct. Why is that? Because essentially the working set concept is sort of only making sense within a process context, right? So you only track the working set for a particular process, right? There is not much a concept for the global, for the working set on a global level, right? You can't really have a working set, um, you know, for your whole system. I mean, I guess you could come up with one, but that wouldn't be accurate for any process, right? So you would only want to track the working set for a particular process. All right, so let's move on to the next topic, the load control, right? This is another design issue with the paging system. So we just talk about, okay, this global and the local allocation policy, and we also have the page replacement, the page fault frequency model. We use that model to track the working set of each process over the time. We can get a very good estimation of the working set size for each process, right? So sort of like so we can find a best way, right, to track the working set for all processes. And then we can also pick a very good page replacement algorithm, right? Let's say we pick the working set clock algorithm, which works really well in a lot of scenarios. Or we can pick the not frequently used with aging. That algorithm is also widely used. That's also a very effective algorithm. So let's say we have the best combination, right? We have the best combination of the page replacement algorithm and the allocation policy, right? Now so with that combination, so we should be good. We should have very few page faults, right, in the system. But in some scenarios, you could have what? If you just keep loading programs into your system, you could end up with what? You could end up with the working sets of all your running processes. The size, right? The size of the combined working sets of all your running processes is simply bigger than your physical memory, right? Right? So if that's the case, you're gonna end up with some processes not having enough memory for their working sets, right? So in that case, you're still gonna have a lot of page faults, right? Make sense? So it's essentially, you just don't have the bare minimum physical memory to host all the working sets, right? For all your running processes. In that case, you're still gonna have like this overcommitted memory scenario, right? So with that, you would also have thrashing. Thrashing is simply the term for in a multi-programming environment, you don't have the minimal physical memory to work with for all the processes you're running. So then you will end up with a lot of page faults. Okay, so one of the solution could be, you just have to swap out some processes, right? Because you just simply don't have enough memory, physical memory for all these programs to run. So you just have to swap out some processes. So that could be a solution. There are two ways you can swap out the processes for solving this load control problem. One is that you could periodically throw out some processes, right? or you could throw out, you could not throw out, swapping out. You could swap out some processes based on your demand at that particular moment, right? So, sorry, I didn't have the other swapping out scheme written here. So you could have periodical kind of swapping, or you could just swap out some processes based on the demand at that particular moment. So, all right, that's quick enough. So let's move on. So we just talked about some design issues for paging systems, and now let's move on to the implementation issues for a paging system. All right, so we need to walk through the detailed steps of handling a page fault. Okay, this is important, so you may want to pay special attention to this. So we want to know what exactly is happening when your operating system is handling a page fault. So when page fault occurs, right? We talk about, for any of these any of this kernel level processing, like a page fault handling, it needs to be in kernel mode, right? So first, when you have a page fault, how does your system handle it? It needs to trap into the kernel mode, right? So essentially, it's your operating system does the handling for page fault, right? So your operating system, who reports the page fault? Who can tell me? Who reports the page fault? Anybody has any idea? When you have a page fault, your architecture, right? Your architecture needs to report the page fault. In this particular case, we talked about this before, on your hardware, you have your hardware support in memory management unit. So memory management unit usually is part of your CPU or a separate chip, right? In the hardware. So memory management unit reports the page fault when it occurs. And then the system will trap into the kernel, and your operating system will take over to handle the page fault. All right. So the first thing is your CPU will try to save whatever is going on at that particular moment, right? When the page fault is happening. Okay. So it needs to remember, right, whichever the instruction in progress at that particular moment. That's the very first thing. So then we talked about this before. When you trap into the kernel mode, your process that is executing that instruction that triggered the page fault will be what? Will be suspended, right? So when you suspend a process, right, that later on you need to restore it, right? After you handle all these, the page fault handling, you would put that process back to the ready queue to be executed in the future. So when you suspend the process, you need to save the context, right? What are the contexts we talked about before? Is essentially, on the hardware, you have all these registers, right? When your process is executed, you need to save whatever the register values at that point for your process, right? Things like the program counter and the stack pointer, the heap pointer, right? And essentially, and all your memory related information or file related information, right? One of the memory related information, I didn't put it here, would be your cache information, the TLB. Remember when we talk about TLB? TLB is what? TLB is the cache for caching what? For caching the page table, right? Page table is the translation between the virtual page and the physical page, right? So TLB information could be part of the context information saved. Where do you save the context information? for all your processes? The process control block, right? Remember that, right? The process control block is the main data structure for saving all your process related information throughout the execution. All right, so then after you save all these information for your process to be suspended, then you need to find out what? You need to find out the interrupt routine, right? Interrupt service routine to handle this page fault, right? How do you find out the interrupt the service routine? You go to the interrupt vector, right? As you guys did in your assignment, right? Essentially, the interrupt vector is what? Is a lookup table, right? You just go there. Your interrupt has a number. Here, the interrupt is what? Is a page fault, right? So that page fault, that interrupt has a number. You just go to the lookup table, which is the interrupt vector. You find out the page fault service routine, right? Of course, you would remember like which page actually faulted, right? When you access which page, it incurred a page fault. All right, so next you would want to check whether that virtual address you're trying to access that triggered the page fault, whether that's valid or not, actually, right? So it's not necessary it's a valid access, right? So first you need to check on that. So if the access is not valid, your process is going to get killed by your operating system. You know, things like you're trying to access a read-only page, right? Or you're trying to access some memory address that is you're not supposed to, right? Oh, you know, you guys have had in your programming, you had the segmentation faults. All those faults, they're invalid memory access, right? So your process is going to get killed. So those are invalid access. All right. So you exclude those for, you know, if those are invalid access, and you just kill the process. And then if you find out if it's a valid access, then you need to do what? Then you need to, then this access is what? This access is about you're accessing a virtual page that the corresponding physical frame is not loaded yet. So you need to load that page from the disk, right? So you could, at that particular moment, you could still have some free physical frame to work with, right? So if you do have free physical frame, in the free physical frame pool, you can grab a frame from there, right? Or if you don't, you have to do page replacement. Clear? All right. So in the page replacement case, we just talked, last class we talked about it. You know, what's the process there, right? The idea there is that you want to find the clean page. What is a clean page? A clean page, in the LRU case, all the approximation algorithms for LRU, you want to pick a frame that is not recently used, right? And not recently referenced. And the page is not modified, right? That's sort of a clean page, right? So you have your reference bit and your modified bit, they're both with 0. That's your clean page. If you ever find that page, you throw it out. You bring the new page in, right? But if you find a not recently used page, a reference page, but if that page is kind of modified or dirty, you have to schedule a write out for that page, right? So that you don't lose data for that page. So I won't go through more details on that, but essentially, you need to consider those scenarios in the page replacement. All right. So after you have a clean page to use, and then you throw it out and you bring the new page, right? And then you would put the suspended process back to what? To the ready queue, right? So right? So once you have the suspended process put back to the ready queue, right? Would that process get executed right away? Would that be a guarantee? Yes or no? No, right. Why is that? Because there could be another process being executed at that moment, right? So you simply put that suspended process back to the ready queue. It will be scheduled to be executed later on, right? All right. So this is the whole process of a page fault handling. Okay. All right. So we need to with that uh, the the steps we just went through for page fault handling, we need to, that would be a good segue to the next topic for the implementation issue, is that, when we have a page fault, the page fault could be happening during the middle of executing an instruction. In a normal architecture, in a modern architecture, an instruction could be executing multiple things. And an instruction could be accessing multiple pages just for one instruction execution. Okay? So let's look at this CISC example here. All right. So what if during the middle of execution of an instruction, it incurs a page fault? Right? So it could happen. Okay, so let's look at this example here. This is a simple CISC assembly instruction. So this instruction is essentially does it does what? Actually has the execution kind of has two steps, right? So it does this auto increment, right? Okay, for this R2 register. So it increments R2 register. Then it tries to move whatever in this R2 register to this address. Okay, so let's suppose the incrementing R2 register doesn't have any problem. It just increment the register, right? And then you try to move that value from the R2 register to this address. And in that step, you find out, oh, that address is not in the physical memory. What do? It would incur a page fault, right? Right? So then you do all the page fault handling, right? So you load that page that is not in the physical memory. And then and when you come back here, you execute this instruction here. Do we have a problem here? Yes or no? So will there be a problem if you try to re-execute this instruction? Yes, right? Oh, no? Why is no? Can you? Oh, okay. All right. Okay. All right. If you have anything you want to say, just unmute yourself. Okay. So basically, when you come back here, after the operating system handles all the page fault handling, right? It needs to come back to this instruction, right? It needs to restart this instruction. So if you restart this instruction, obviously you will have a problem. You would do what? You would increment this register again, right? That obviously is a problem. So you don't want that, right? So you would have to do what? You have to do some rollback to deal with this, right? You have to roll back this auto increment for this R2, then you can re-execute this instruction, right? So while that's sort of trivial to do, right? In this little example, it's not always trivial for other kind of operations, right? So this can be easily handled, okay? But what about a block memory transfer, right? So let's have a scenario here. Hopefully I can draw something. All right, so I have said this is the physical memory. Okay, say I want to copy this range of a memory to this range. Okay, so this is your source, this is your destination. Okay, so look at this, they're overlap with each other. If you copy this memory to this destination, right, while in the middle of copying this whole block of memory here, right, of the source, right, to this destination area, if they're overlapped with each other, then when you copy this page, then you copy this page, right? So this page here, that copy process is irreversible, okay? So if you override this piece of memory, you cannot recover, right? So this sort of like an example that this is a not trivial example, this is a non-trivial example that I want to talk about. So some instructions you are executing cannot simply be reversed. Okay, so for this scenario, you have to do what? You have to check before you copy, right, the memory, the block memory transfer. You would have to check whether you do have, you have these memory areas, they're overlapping with each other. So you just have to do more, right, to handle this special scenario. Okay, so these are some of the concerns you have to worry about. All right, so looks like we're out of time already. But let me just quickly finish, what we want to talk. This would be the last topic for this paging system topic we want to talk. So the locking pinning pages, the idea there is that we talk about the page replacement, right? So page replacement, you could just throw out any page, right, with a particular page replacement algorithm. If that page is, say, with a particular algorithm, if that page is not recently used, if that page is clean, not modified, we could pick a particular page to throw out. But it turns out some pages, they're special, right? You probably don't want to touch them. So what are those special pages that you don't want to touch? One of the examples would be the memory space, the memory pages we allocated for DMA transfer. So what is a DMA? DMA is a direct memory access, okay? So remember what we talk about in the architecture support review, the direct memory access is what? Is essentially a special area in the memory your operating system gives the IO device, right? For the IO device to work directly, right? With that memory area. So the IO device can transfer data to that memory area or grab data from that memory area directly, right? That's what we call direct memory access. Okay, so for that piece of memory area, you don't want to touch that. Okay, so basically, the page replacement algorithm needs to avoid kicking out that piece of memory area. Okay, that's one example. So you want to what we call you want to lock those pages, or you ping those pages there, right? And the other example is that a lot of times, say you load some pages, right, into the memory, but before they are even being before they're even referenced for the first time, you don't want to kick them out, right? So you load some new pages. Some operating systems, they do this, for the newly loaded pages, if they're not referenced for at least once, they want to keep those pages there, right? So, you just load them, right? So you don't want to kick them out. They could satisfy your page replacement algorithm criteria, but since they're not referenced yet, you may want to give those pages a chance, right? All right, so that's pretty much according to what we planned for the paging system topics, those are all. So essentially, we finished talking about everything we need for the paging system. You guys have the slides, right? I've already loaded all those to Blackboard. We will give you guys the details on the midterm, okay? It most likely will be next Thursday, okay? But whether we will do it like sort of like as a normal midterm kind of test, we could do some, like I mentioned at the beginning of this class, we could change the exams to a series of small quizzes, okay? Each quiz could include, a couple of topics, right? So you may not have like a major exams, for this for this semester. I talked to Dr. Roche this afternoon about how exactly that we're gonna proceed for the exams. So we will give you more details on those. Okay. So that's why it probably no point to go through the midterm concept anymore, because it most like there is a strong possibility you will end up with a number of small quizzes. Each quiz would not test you a whole list of concepts. Each quiz would just test you a few concepts. Okay, and again, next Tuesday will be your submission for the due date, the new due date for the assignment 4. All right. So any questions, guys, before we end today's session? Anybody? If you're talking, I can't hear you.
I don't know if I missed this, but did you say the recordings would also be on Blackboard of the session?
Yes. I will try to. I'm recording this. Oh, like I need to. Sorry, I need to. I need to stop recording now. So